So the first thing that we need to understand when we're studying vector calculus is curvilinear coordinate systems. It sounds kind of like a big word, but the concept it represents really isn't that difficult. So what are we doing here? We have a coordinate system in which we have 3 dimensions of movement: the x direction, the y direction, and the z direction. We want to be able to pick a point within these 3 directions of movement. So let's go ahead and do that. I'm going to go ahead and pick here. This is going to be our point. What does that point mean to us? That point means if we traveled this much in the x direction, and then we traveled this much in the y direction, and then we traveled this much in the z direction, we would have a point here that we could tell somebody the location by saying, I'm at x, y, and z. Now, this is going to be the typical representation for a location in Cartesian because the axes are labeled x, y, and z. There are unit vectors in which we assume the unit vectors are orthogonal to one another. So let me go ahead and draw those. I'll use a different color. So we've got these little guys. Unit vectors, one in the x direction, one in the z direction, and one in the y direction. These are the basis for our Cartesian system, and what they do is they tell us this is the y direction, this is a unit length 1 in the x direction, this is a unit length 1 in the y direction, and this is a unit length z in the z direction. If this total length here in the x direction is actually like 3 units long, what I'm saying is this length is 3 of the x unit vectors, because we set up a system in which when we translate our location to other people, they're going to be assuming that the base unit for each of the x, y, z is in terms of the unit vectors, which if for some reason we chose like 3, maybe like 5, and then we'll say like 3 again, like if we chose that, they would know there was 3 unit vectors in the x direction, 5 unit vectors in the y direction, and 3 z hat unit vectors in the z direction. Typically we just write those as whichever direction it is with a little hat on it. So z hat, y hat, and x hat are the blue unit vectors. So similarly to the first way we express the location of some point in within this 3D volume, we can also say if we already have a point x, y, so x, y, z, so we'll go ahead and choose this one. This is our x, y, and z in terms of x hat, y hat, and z hat. Once again, we can say, let's choose another point over here, which is that x number plus some small change in it, that y number plus some small change in it, and that z number plus some small change in it. We can actually relate these 2 points from here to here by something we call a displacement vector. Most times you'll see it represented as this, some change in length. This L represents length. This little signal just lets us know that it's a vector. It is represented as some value times the change in x in that x direction plus some value times the change in y in the y direction plus some value times the change in the z direction. So some value multiplied by the change in the z direction multiplied by the unit vector to let us know that this is in terms of unit vectors. And why this is important, it's because it helps us translate between different coordinate systems. For example, in the Cartesian coordinate system, the one that we've been doing, we've been saying let f, g, and h all equal 1 so that we can describe a change in length as just the change in x in the x direction plus the change in y in the y direction plus the change in z in the z direction. And if we go ahead and look at our choices up here, we had x, we had y, we had z. We're calling this guy here dl. And assuming we want to change like from here to here, or however we're going to be changing it, it looks like the change from the original is just dx in the x direction, dy in the y direction, and dz in the z direction from the original point. Just for right now, I'm going to go ahead and let you know that in the spherical coordinate system, we're going to have this f equal to 1, g is equal to r, and h is equal to r sine theta. And what that means to us is r direction, which means some distance radially out from the origin. Then we're going to have a theta. Since we're physicists, we're going to call our theta from our z to our y. And our phi goes from our x to our y. Now I'll choose a different color and do another common coordinate system. Let's go ahead and do the cylindrical one. F and h are both equal to 1, and g is equal to r. And so what that means is, similarly, we have a r, we have a phi, and we have a z. So it makes it into like nice cylinders like this. So therefore, if we're going to be looking at dl, some change from maybe like here to here, and we're going to be looking at it in terms of the position characteristic of a particular chosen coordinate system, we said that we're going to write it as dl equals f dx in the x direction plus g dy in the y direction plus h dz in the z direction. For Cartesian, we said that f, g, and h are equal to 1. So we can go ahead and write the dl as dx in the x direction plus dy in the y direction plus dz in the z direction. Now, for spherical, and you're going to have to trust me on these translations because I'm going to do individual videos proving why the FGH are why they are what they are. And those are kind of lengthy proofs, so I'll do those in each of their own videos. But for the spherical, we have dl is equal to, if f is 1, then we're going to have, since we're talking about r, phi, and theta, it's going to be in terms of these. So we say that this translates to this one, and f is 1. So we're going to have dr in the r direction plus, we said that g is r, so we look at this dl and we say g is r d phi in the phi direction, and we said that h is r sine theta, so r sine theta in the theta direction. So that's how you translate between two points given a small path length dl in spherical. And similarly, I guess I'll do the last one in green. We have the cylindrical, so dl, and instead of x, y, and z for cylindrical, we have r, phi, and some z, where we say that f is 1, g is r, and h is 1. So we have dr in the r direction plus r d phi in the phi direction plus h is 1, dz is dz, so we just have dz in the z direction. Okay, and I'll just write this so these are cylindrical, this is spherical. And just once again to further elaborate, so the x unit vector is like this, the y unit vector is like this, and the z unit vector is like this. Now, we have other unit vectors for other coordinate systems, obviously, just in case some of you are confused by some of these. So r is some vector coming out like this, pointing radially outward from the center. X to y is phi, and z to y is theta. And finally, so we have r, we already know what r is, we already know what phi is, and we already know what z is. So each of the unit vectors in these three different coordinate systems have been accounted for, and now you know how to represent a path length in any of these three coordinate systems, although the proof will come later.